Hello and welcome to this video comparing the impact of the long-term culturing of a commercial yeast strain. There is a long-running argument that yeast should be fresh, new, and from a reputable supplier. This is supposed to provide the best results. The alternatives consist of wild yeast from the ingredients or air, reviving yeast from past batches, or as we will show here, propagating a conventional yeast source to increase your stock. The basic process of brewing is to combine a suitable saccharide, water, and yeast. This is then sealed in a vessel where oxygen cannot intrude and carbon dioxide can be expelled. This facilitates fermentation. The limiting feature of brewing is the amount of sugar and the longevity of yeast in it before it flocculates. This is influenced by temperature, pH, nutrition, and importantly for this video, the health of your yeast. Unhealthy yeast cannot effectively metabolize saccharides into ethanol. It readily flocculates, produces off flavors, and may not be able to ferment at all. This can be due to a variety of factors, but the most important ones are those relating to mutations. As with any organism, the longer it lives and the more generations that occur, the more damage that is inherited. In humans, a generation takes roughly 20 years. With yeast replicating every 12 hours, this is one of the faster growing organisms on Earth. That means 2 generations every day and 2 replication events that can cause mutations. 2 generations a day, 14 generations in a week, 60 generations in a month, and 732 in a year. This means many opportunities for mutations occur and have ample opportunity to be passed on to the next generation. This is why the common wisdom is not to propagate your yeast. It may acquire traits that are undesirable or lose traits that are desirable. We are therefore testing this idea. The approach is quite simple. To begin with, how much CO2 is generated by yeast that has been cultured over a given period? How much weight is lost in the fermenting vessel, and is this comparable to the original sample? We did this by culturing a high ethanol yeast tolerant strain every 12 hours. This was a combination of yeast culture, flour in order to give us bulk and make it easy to work with, sugar, and water. Each week, yeast nutrient was added to this. We then took these samples over the period of roughly 9 months and prepared 5 vessels. We then ran this experiment 3 times with each of the values given later and average of the 3 runs. We used an original yeast strain that is meant to produce high concentrations of ethanol. This should remove the upper limit of ethanol tolerance. That can be done because we are not using enough sugar to produce a high between 15 and 20% ethanol product. Rather, we are aiming somewhere considerably lower, in the hopes of simply getting a good indication of what its capacity is. We've taken a new sample of the strain being tested. We've used a 1-week culture, a 5-week culture, a 10-week long culture, a 15-week-old culture, and one that is coming on 9 months by the time we've taken a sample. These were prepared, mixed, bottled, and an airlock was used. The airlock was sealed with the balloon and tied tight. This allowed us to capture the CO2. Each of these was left to run for a week. Over the period of the 3 weeks we ran this experiment, we were able to collect the data you see plotted. Before and after the experiment, we took appropriate measures of the weight. Primarily, we focused on the weight of the whole of the setup. We then allowed for the weight of the fermenter and the airlock, and we were able to subtract the weight of the airlock from the final weight measured. This gave us a weight of CO2. We were able to use displacement of water to figure out the volume of CO2 captured, and when adjusting for air temperature, we can get a final volume and translate this to a mole or molecular weight of the CO2 we have on hand. Knowing how much sugar went into the fermenter, how much CO2 was produced, we can figure out some degree of efficiency. This, in combination with specific gravity and other measures, allow us to figure out just how effectively the yeast worked. What we see from this experiment is interesting, but honestly it is rather predictable in the final pattern. There is a general trend towards less performance. We measure this by the difference in the first weight with sugar, yeast, water, and so on, and the final weight where the sugar has been fermented out of the mixture. We can see that having taken away the weight of the CO2, there's been a small but constant loss. This is improved with the earlier samples but deteriorated over time. We note that after a week, performance is comparable to that of the original sample, so it could be argued that in the short term, culturing of your yeast is unlikely to adversely affect performance in the current arrangement. This was not necessarily a clear-cut relationship over the roughly 9 months we have been testing the yeast. That's because we've allowed for the first 15 weeks and then we've jumped to the final sample. Perhaps we should have designed it in a way that accounted for every week or a slightly better distributed period, but over the 4 weeks that are directly related to each other and in proximity, we can see a general trend towards less productivity. That means our relationship is not necessarily clear-cut, but there is definitively a relationship. We're hoping we can develop an appropriate model later on that will allow us to figure out just what that is, as it is clearly not linear. When we look at the amount of CO2 produced as a ratio of the yeast concentration, we are getting a better and somewhat clearer image as to what is going on. As our original sample was a dry sample, we had to compare this to a wet sample from the cultured yeast. By allowing for a weight-to-weight ratio, we can figure out just how much CO2 and as a consequence how much sugar is being fermented for every gram of yeast you are introducing. In this case, the closer to the blue mark or above it, the better the yeast has performed. You can see how initially the two are very close together, but over time they grow further and further apart, clearly getting worse. We can see that here, and there's no real way to argue around that. What we should explore at some point is to see just how close that separation is over the first week, or perhaps the first few weeks. Barring that, you can see that the sample from the industrially produced yeast is performing best. That, as time goes by, the yeast performs worse as each generation passes. This is a direct measure of the weight of CO2 and the volume it has displaced. This is also supported by a trend in the estimated ethanol content. We get this estimate by taking the initial specific gravity and the final gravity measurement and figuring out how much ethanol should have been produced by the change in the displacement. There is again a general trend towards less ethanol with age. The difference is not huge, but it is noticeable. Over the linear portion of our test, that is the initial weeks 1 to 15, we see a loss of about 0.5% of ethanol yield. This trend matches with the pattern we see with CO2, although not exactly the same delta. You'll note that over the final sample, which is our 9-month culture of yeast, there's a drastic difference, and the loss there is far more significant. This is a general and simple design for our experiment, and it is flawed. However, despite the flaws in it, it does show a diminishing return on age if you keep culturing a yeast sample as we have here. That is not to say the loss is equal or linear at all times. It is possible that over the period of the first 4 to 5 weeks you may appreciate the increase in volume of yeast despite the loss in its productivity. There may be a tipping point at which you are happy to consider some decrease in efficiency in lieu of the ultimate cost of getting more yeast. When considering that, our current design is not an ideal model, and we need to address some of the limitations that contribute to that. First and perhaps foremost is the way we've stored it. Our yeast was simply stored in a frozen environment after it had reached 12 hours post being fed. That is, we would culture the yeast, allow it to reach its peak division at 12 hours, siphon off the necessary portion into the new culture, and then freeze that week's sample. As you can imagine, over such an extended period, our cell culture as such may not have experienced the most hospitable of environments. This means that after 9 months, there may have been some degradation, and we would need to consider just exactly what has changed over that time. There is also the way that we've relied on 3 samples of an experiment that's been repeated. That is, there's roughly a week between each of the measures used. There is possibilities that some environmental variation could have occurred in that time affecting our results. In the short version of this experiment, we would ideally be able to have a completely controlled environment, but we do not expect to see drastically different results from what you observe here. With that in mind, we will look to continue to propagate this yeast sample and test it after 12 months. This will allow us to see how far the original has moved from the cultured yeast stock. 12 months, remember, is over 700 generations that have passed between the original industrially generated yeast and what we have continued to grow. It'll be interesting to see if we see the same general trend towards reduced performance, or if there's a point at which it reaches a ceiling of sorts, a cap to the final way in which it can only achieve so much. Hopefully this has given you some idea about why new, commercial yeast is generally suggested by most serious brewers who have not developed their own yeast or have been culturing samples for a long time in a more structured and rigorous manner than we've been able to demonstrate here. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions below.